The guy who made the periodic table.
That's right. You know who that is?
Oh, darn.
He's the man. I mean, he's like one of the
He was a Russian scientist, right?
Mm-hmm. Yep.
Yeah, he went to like
can't-
that Petersburg University, whatever.
Yep.
Ah.
He's a hero in Russia and pretty much everywhere else.
Oh, come on. I got this.
Mendeleev. There you go. Dmitry Mendeleev. And he's basically, there's a lot of really interesting things to say about Mendeleev, but I may save it for the next chapter. Because it was he and actually a German scientist who basically came up with how to arrange. There's been lots of attempts to arrange the elements into some sort of table that would sort of predict things. And although he and this other German scientist basically came up with the same idea at the same time, it was Mendeleev who really pushed it and made some predictions that would prove to be, right on about things that he knew nothing about, like electrons and protons and neutrons, which are completely unknown. Because remember, he came up with this around 1870 or so. So yeah, there was very little known about chemistry at the time. So we're going to learn about what a chemical element actually is, learn how abundant some of them are. You probably have some ideas of which ones are really abundant and which ones aren't. We're going to learn the different chemical symbols. You're not going to have to memorize them because hopefully everyone has printed out their periodic table that I put on Canvas. So this is also something that you will have during a test, and you can refer to it at any time because no one is expected to memorize the atomic weight of chromium. That's just a ridiculous waste of your time. So have that with you. In fact, if you can either print it out or something like that, when doing the problem sets, it'll make your life much, much easier. Learn about how an atom is constructed, the three main subatomic particles. If you want to get really deep into weirdness, talking about what particles make up the main subatomic particles, like quarks and muons and all kinds of string theory, you can get just incredibly deep into this. And the smaller you go, the weirder it gets, believe me. We'll learn how these subatomic particles are arranged and give an idea of how that affects everything in chemistry. And I sort of promised we'd be talking about radioactivity, since some of you are going to be going into working with radioactivity in the lab, radiology. So we're going to talk about that tonight as well, and how it's used in the medical field. So here's what the sort of basic breakdown of the periodic table looks like. And it may have been a while since you've looked at it, but you can see that it is sort of broken down into three general types of element.
Oh, you muted yourself, Professor.
Am I back?
Yes.
Okay. Okay, all right, I just want to be able to write. Here we go. Yeah, so we have nonmetals, which are on the right side of the table. And we'll learn a lot more about nonmetals coming up. Nonmetals tend to gain electrons and become negatively charged. Metals, or the vast majority of elements, are metals. Almost everything is a metal, which is weird when you think about it. But all of these elements, all of them, all metals. And metals tend to give electrons away and become positive. And then you have these weird things that are sort of in the middle. And when you look at your periodic table, you'll notice there's basically like a staircase over here. And that staircase basically breaks up the metals and the nonmetals. And we call those either semi-metals or metalloids. And And we call them that because they have some properties of metals and some properties of nonmetals, but they're not, you can't call them either one. They're sort of in the middle. And the more we learn about how the atom is constructed, the more hopefully that'll make sense. The other thing to remember is that the rows, we have rows going across like this, we call those periods. And elements in the same period basically are adding one electron at a time as we go across. They get bigger by one. And these go up and down, the not the rows, but the columns are called groups. And the interesting thing about groups is that they're very, very similar chemically. Like, anyone know what the group is in the very right-hand part of the periodic table?
Noble gases?
That's right, excellent. That's where the noble gases are. And noble gases are called that because they're extremely unreactive. They don't really react with anything until you get to the really big ones. And therefore, they're all very, very alike chemically. And we'll learn basically in the next chapter why that is. And it's because they have a full set of electrons. And when elements have a full set of electrons, they don't want to share them with anybody. They don't want to have them pulled away by anybody. They're just stable. They have a full set. We'll learn that that's basically all of chemistry. It's just elements looking to get a full set of electrons. Yes, question.
That excludes helium, right? Because helium only has two.
Nope, helium is a full set as well.
Oh,
Yeah. We'll see that these periods that go across basically tell you how many electrons there are in each level. So as we go across the first level, let me clear this out. This is going a little bit beyond what I was going to talk about, but it's interesting. So as we go across the very first, you can see there's only two elements there, right? There's hydrogen here, and there's helium here. So in the very first set of elements, there's only two electrons needed for a full set. Then we go across the second, there's 1, 2, 3, 4, 5, 6, 7, 8. That means a full set of electrons for the second group is 8 electrons. Same for the third, 8. But then when we get to the fourth, 16. And you can see that there's a pattern developing here. Now, Mendeleev saw this pattern. He didn't understand that it had anything to do with electrons, but he saw that there was a pattern. So what he did was he took elements that react similarly to each other and grouped them together. So we'll have a look a little more closely about what he was looking at. So each block has a different element in it. That makes sense. You already know the vertical column is a group, and they're similar chemically. And we'll learn the name of some of these groups. We already know noble gas, noble gases. We'll also learn alkali metals. We will learn about halogens. And we'll see that like these metals basically can completely substitute for each other because they're very, very similar, easy for me to say, similar chemically. So each of these groups has a number and a letter, and there's 18 columns going across from left to right. If they have an A with them, they're called main group elements. Now, main group elements are called that because they always, those elements always behave the same way chemically. They always either give the same number of electrons or take the same number of electrons in every single reaction they do. Now, the B designations are for transition elements. Now, let me just go back for a second. the transition elements, are the ones here in the middle. It's these elements in here. Those are all transition elements. Anyone know why they're called that? So if the
Is it
main
because
group,
they're
oh,
changeable?
what is that?
Is it because they're changeable?
They're changeable. Yes, exactly. The main group elements always have the same charge. Either they're negative or they're positive, and we'll learn more about ions, because negative and positively charged. We're going to do a little bit of that tonight in the group work as well. But when elements lose electrons, they become positive ions. When they gain electrons, they become negative ions. And the main group elements always form the same ions. They're either always +1 or they're always +2, or they're always -1 or they're always -3. They're always the same. Transition metals can change their charge. They can be a variety of different ones. For instance, iron, which is known as Fe, can be +2 sometimes and be +3 sometimes. And so transition metals can change the number of electrons they give away, depending on who it is they're binding and what sort of reaction they're in. We'll learn a little bit more about that in the next chapter as well. So the horizontal row, known as a period, there's 1 to 7 of them. And the sections of period 6 and 7 are at the bottom. So I'll show you these. These are the ones down here at the very bottom. And basically, they're put there because they're so long that they have 16 elements in each row, that if we put them in, the periodic table would be just insanely long. And these metals are really, really rare anyway. And so we don't really deal with a lot of them, and pretty much all of them are radioactive. And so people don't generally, do a lot of work with them, although there's some really important ones in there like uranium and plutonium and, stuff like that you can make bombs with. So, I mean, they're important elements, but we just generally don't come across them in the lab very often. So to keep the periodic table from being just insanely wide, we basically just sort of leave them at the bottom. So the staircase line, remember I said that there's a staircase basically between, oops, didn't want to do that. There's a staircase basically between the metals and the non-metals. Those are the metalloids. And the only one that's on that line that isn't a metalloid is aluminum. Aluminum is also not a transition metal. Aluminum always makes a +3 ion when it's charged. So it is clearly a metal. As if you've flown in a plane, it's probably made of aluminum. So it better be a metal, right? And let's talk a little bit about the metalloids in a minute, because there's a very, very important metalloid that's responsible for, I don't know, maybe a quarter of all the jobs in this area. Anyone know what that might be?
Silicon.
Exactly right. So I was going to just sort of mention silicon a little bit, since it's so damn important, especially around here. So these are some of the names and symbols for the metals. You don't have to memorize them, although there are a couple that they're just weird when you look at them. Most of them have English or French or names that you can basically figure, aluminum, okay, Al, that makes sense. Argon, Ar, all right, that makes sense. But then you get down to copper is Cu. Like there's no U in copper. Or gold is Au. And sodium is Na. Where do these things come from? Well, those come from because those elements were discovered so long ago that I think the original number of elements, like for about 1,000 years, was around 12 to 16 elements were actually known. They were isolated and people knew about them. So Gold obviously has been around for thousands and thousands of years because basically you can find it as gold. Gold is pretty non-reactive. And so when you're like mining for gold, basically, a lot of the time you just find gold, like a big gold nugget with pure gold. And same goes with a lot of the other shiny metals. Like silver has been known for many, many years. Copper has been known for many, many, many years. And so those names are derived from their Latin roots. Like sodium was called natrium back in Rome. Gold was called aurum. And that's why we have Na for sodium, Au for gold. That's why we have K for potassium, because it was called calcium originally. Silver was argentum. Tin, can't remember what tin was called. But one of my favorites is tungsten, has a W, and that's for wolfram, because it was a German who discovered it and got to name it. And so they got the symbol W for wolfram, which is that's just a kick-ass name, wolfram. So a lot of these you're just going to know because there's some we're just going to be using over and over and over again. Like the most important ones to remember: carbon, fluorine, super important, hydrogen, obviously, iron, iodine. It's not iodine, it's iodine. We call it iodine because it's in the same family with fluorine and chlorine and bromine. So we call it iodine, even though most people call it iodine when you go to the store or something, a tincture of iodine or whatever. It's actually pronounced iodine. So these are just some of the ones we'll be using over and over and over again. So here's our periodic table. And you can see, as I mentioned, these are the transition elements in the middle. So you can see that there is a big gap between the main group elements, which are here, these two rows, and these elements over here. The rest are all transition. They can be a number of different charges. This first group right here, called alkali metals, they're all similar in the fact that they all make a +1 charge when they all lose a single electron. They all have 1 electron in their outermost orbit. And so each one of them tends to lose that electron and become positive. The other interesting thing about these metals, anyone know what happens when you throw either sodium, potassium, or rubidium into water?
It reacts, it blows up basically. Right?
They explode, that's right. Yeah, because they want to give away that electron so bad that when they come into contact, basically you have to store them under oil. They can't have any water around them, because if there's any water at all, they will give that electron to water and boom. So, and the bigger the atom, the greater the explosion. So cesium should give you a really, really big kaboom. Generally, there's not a whole lot of cesium around, so it's kind of a waste of it to make it explode. There's a whole bunch of sodium, so you can watch YouTube videos on sodium all day. So this next one, alkali earth metals, this group here, number 2, it's called group 2 because it has 2 electrons in its outermost orbit, and it loses both of them when it becomes an ion. So when it loses both of them, it forms a +2 charge. And all of these ions form +2 charges: magnesium, calcium, strontium, barium. They all make +2. And then when we come over here to the non-metals, instead of losing electrons, they generally gain electrons. And so as we go across, everybody basically wants to get to the magic number of 8. And so carbon is in group 4, and it gains 4 electrons and becomes -4 charge. Nitrogen in group 5 wants to gain 3 more electrons to get to 8. So it becomes -3. Oxygen is in group 6. It also wants to get to 8. And so it gains 2 electrons and becomes -2. And then finally, the halogens here, they all have 7 electrons in their outermost orbit, and they want to get to 8. And so they're really good at stealing electrons. We'll learn that there's a property called there's a property that these electronegativity, that these elements have very high values of. And what that means is they can steal electrons from basically anyone. Fluorine is the strongest element at stealing electrons from people. So basically fluorine will become negative and steal electrons from any other element. In fact, fluorine is so strong at stealing electrons, it can even steal electrons from noble gases. It can form compounds with krypton and xenon because it could steal electrons very, very readily. But it only needs 1 because it already has 7, so they become -1. Now, the element I sort of said I want to just sort of touch on briefly is silicon here, right here in the middle. Now, silicon has properties both like a metal and like a non-metal. What can metals do with electricity? Are they good conductors of electricity or poor conductors of electricity?
Good conductors.
They're really good conductors of electricity. In fact, that's one of the main properties of metals, that they're such good conductors of electricity. Non-metals are crappy conductors of electrons, basically because they want to just hold on to electrons. So non-metals hold on to electrons, and so electrons don't flow very readily through non-metals, very, very poorly. Silicon is right in the middle. That's why it's called a semiconductor. So what that means is that electrons can flow through silicon, but poorly. They can flow, but not great. And why that's important in the semiconductor industry, if you want to count electrons, you can't have them moving so fast. So silicon is perfect in that electrons will flow through it, but a little more slowly than it would flow through a metal. And that's what makes it perfect for building, silicon chips and micro wafers and computer parts and all that stuff, is because it holds on to electrons just long enough to count them and then lets them go. Whereas metals just let them go entirely, and non-metals just hold on to them and don't let them go ever. So that's why silicon is so damn important. Right, let me check the chat to see if you can. Oh man, you guys are, I love it. You guys are chatting about your own understanding of all this stuff. That's excellent. Okay.
I thought carbon was more about, sorry to interrupt. I thought carbon was more, when you said that it gains electrons, because it's 4. I always thought carbon had more, in terms of bonds, it had more covalent bonds. It would rather share it rather than
you're absolutely right. It normally shares 4 electrons to get its full set of 8. You're absolutely correct. That's in fact part of the next chapter, dealing with the differences between ionic bonding and covalent bonding. You're way ahead of me. Yeah, so carbon very rarely is an ion, but it can form an ion. You probably heard of carbide. Carbide is a carbon ion. And so if you have something like tungsten carbide, that forms like incredibly hard, like drill bits are made of tungsten carbide. Tungsten is already like really, really hard metal, but if you get it to form a complex with carbon, then it's insanely strong. And so you're absolutely right. Carbon usually, like 99% of the time, is sharing electrons. We all like to share, but some of the times it can be put into positions where it forms an anion. And when it forms an anion, it has a -4 charge. But yeah, nice catch on that. So carbon, as you see, is pretty much there's a ton of carbon in you right now. I mean, carbon is the most important element for us, clearly, because I mean, we're basically a carbon skeleton from head to toe. But there's also a ton of hydrogen atoms in our body. Pretty much every molecule in your body has some hydrogen in it. Oxygen and nitrogen as well. They make up most of the biological molecules are going to have all 4 of those in there. You're also going to have sulfur, and you're going to have phosphorus as well. Those are also present in almost every biological, like large biological molecule. So we call elements that we need in quantities greater than 100 milligrams per day. So what's another way of putting 100 milligrams? How many grams is that? How many
100?
grams in 100 milligrams?
Oh, how many grams? 1, right?
Nope.
Or is it? Give me a sec. I think.
Milli means 1,000, so 100 divided by 1,000.
1,000th of a gram. Like so, 10th of a gram. Yeah.
1/10 of a gram. So you don't need a whole lot of these, but you do need to have them replaced every day. So you need sodium, magnesium, potassium, calcium, and chlorine. So sodium and potassium, basically you're going to find sodium outside your cells and potassium inside your cells. And they're there on opposite sides of a membrane for a reason. That's basically how the cell generates energy, is by moving electrons one way and another. So sodium you have to have a gradient of sodium from high on the outside to low on the inside, and calcium the opposite, or potassium the opposite, high on the inside, low on the outside. Calcium, we all know, need them for our bones and teeth. Chlorine basically is the other ion found with sodium and potassium. Chlorine forms chloride ion with a negative charge. And then you have these micronutrients that you don't need much of at all, but are still super important, like iodine. Anyone know where iodine goes in your body? Where's the main place you're going to find iodine?
Hormones.
Which one?
It's also radioactive iodine. It's also commonly used for thyroid cancer.
Exactly. We'll find out a little bit later. Yeah, that's the main purpose of iodine, is it forms thyroxine, or thyroid hormone. So that's one of the reasons why iodine was added to table salt, because people who lack iodine in their diet get these goiters, right? These huge goiters on their neck. They don't have enough iodine to produce the thyroid hormone that they need. So that's why that's included with salt. You desperately need it. And you're absolutely right. We're actually going to see that with radioactive iodine, you can see, you can image the thyroid, and you can also see how quickly it's turning over iodine. A healthy thyroid will be turning over iodine quickly, and if it's not working well, it won't be turning it over as quickly. You can actually just count how fast iodine is going in and then leaving. So you need fluorine, you need iron. Iron is super important. You wouldn't be able to breathe without it. Hemoglobin has iron at its center, and it's oxygen binding to iron and then being released by iron, which allows you to breathe. So I would say iron is kind of important. So this is sort of, everyone's probably familiar with hopefully what an atom looks like, where you're going to find, what are the different subatomic particles and where you're going to find them. So we have 3 basic ones everyone's probably familiar with: protons, neutrons, electrons. The two of them are found inside the nucleus. So in an atom, you have this super, super, super small structure in the middle called the nucleus. So there's the nucleus in the middle, and it is super, super tiny as far as the atom goes. And I think it's the equivalent of having a tennis ball at the 50-yard line in a football stadium. That would be the size of the nucleus compared to the size of the atom. So it is super, super small. And then that is where you'll find protons. You'll find protons there, and you'll find neutrons there. The electrons you're going to find outside the nucleus, spinning around it. And that part of the atom is much, 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 much bigger. So there's a big distance between where the electrons are and where the nucleus is. So the electrons, you probably know by now, are negatively charged. Protons are positively charged. And neutrons don't have any charge. And we'll find out a little bit later why that is. So atoms, to be called an atom, you have to have no charge. So an atom, by definition, has no charge. So it has to have the same number of protons and the same number of electrons, since they're the only ones carrying charge. Neutrons aren't involved. You can have as many neutrons as you like. It's not going to change the charge of the nucleus. So the positive charges are centered in the middle and the negative charges around it. I think everyone's probably familiar with that. And so it's this. People didn't understand this for the longest time because it doesn't make sense. Like, why would positive charges be all bound together like that in the nucleus? What do like charges tend to do to each other? If I have two positive charges and I move them together, what's going to happen?
You're going to repel
They
against
repel?
each other.
Yeah, they repel each other.
Yeah.
So for decades, after the nucleus was discovered, and then it was also discovered to have a positive charge, that just blew people's minds because that doesn't make any sense, right? You can't put positive charges together, they'll fly to pieces. And it wasn't until we came up with the idea of the strong nuclear force, which is one of the 6 basic forces of the universe. Ooh. The strong nuclear force is basically, that's the glue that holds these positive charges together, as well as the neutrons as well. I'm not going to talk about the strong nuclear force. That's for physics and weird people who study that sort of thing. So these are the properties of these particles. So these are the symbols. So P with a plus sign for proton. Neutron is just an N with a naught or 0 to show you that it has 0 charge. An electron we just make like that. Electron with a negative sign. Sometimes you put it like that, sometimes like this. It doesn't really matter. But make the E with a dash for negative. Now you can see the mass, they're super, super small, really, really, really small. And so we've come up with something called an atomic mass unit, or AMU, because it's kind of tough to refer to this all the time. So we basically gave protons and neutrons a mass of 1. You're 1 mass unit, because we can't be writing 1.673 times 10 to the 27 kilograms all the time. That takes forever. So we're going to call you 1. Neutrons, actually a little bit more than 1, which we'll see in a little while. And electrons are super, super tiny. They're only about 1/2000th the mass of a proton or a neutron. They're super, super, super small. And then so the relative charge, +1, 0, -1. That's really the key things. The mass, 1 for protons, 1 for neutrons, and hardly anything for electrons, and the charge. It's really the only things you need to know about their relative properties. So just like I said, the AMU, we use the atomic mass unit when discussing the mass of atoms, because the mass of an atom is so incredibly small that will just sort of just made everything relative. It's like, okay, yeah, they're all super, super tiny. Can we just talk about like 1, 2, 3, 4, 5, rather than use this incredibly small mass? So it was defined as 1/12 the mass of a carbon atom is an atomic mass unit. For years and years and years, it was the mass of hydrogen, because hydrogen has 1 proton in the middle and 1 electron going around it. So for a really long time, the atomic mass unit was the mass of a hydrogen atom. And in biology, it still is. We call it a Dalton in biochemistry. We still use that. But in chemistry, we've changed it to 1/12 the mass of a carbon atom. And not just any carbon atom, but carbon 12. And we'll learn what that means in a minute as well. So protons and neutrons each weigh 1. And the mass of an electron is so small, we just basically say it's 0. Although obviously it has a mass, it's just super, super, super small. So burrowing down, here we have a piece of lithium metal. Lithium is super, super light metal. So that's what the metal looks like. And then so if you zoom in a little bit further, this is what the lithium atoms would look like. They sort of pack together. Metals have a distinct way of bonding. And we call these actually, it should be easy to remember, metallic bonds, which are different from bonding with metals and non-metals, or the way non-metals bind together. When metals come together, they basically share their electrons freely. That is why they're such great conductors of electricity, because they're already sharing their electrons freely with each other. And so electrons can move through it very, very quickly. So if we zoom in even closer to these atoms, you can see that we have the middle. Here we have the nucleus, which has 1, 2, 3 protons. So, and 1, 2, 3, 4 neutrons. You'll see that as elements get bigger and we add protons, we add even more neutrons. And that's something to do with nuclear physics that's like way beyond me and the scope of the class. But the ratio of protons and neutrons are basically what controls radioactivity. And so elements that have too many neutrons or not enough neutrons tend to be unstable and their nuclei breaks down. And we'll talk about that a little bit at the end of the chapter as well, because this is where radiation comes from. Radiation comes from the nucleus. So then around the nucleus, we can see there's 1, 2, 3 electrons. So if there's 3 protons, and this is an atom, there's got to be 3 electrons. So there's no net charge. So when lithium is just hanging out with itself, being a metal and all, it has the same number of neutrons, or same number of protons and electrons. When it becomes an ion, it loses some of these electrons and becomes positively charged. Like the lithium you would take as a drug, for instance. That's lithium, that's a lithium ion, lithium plus, Li plus.
It's for bipolar disorder.
That's right. Atoms of the same element always have the same number of protons. So that's the way you can tell 2 atoms are the same, if they have the same number of protons. They don't have to have the same number of neutrons, and they don't have to have the same number of electrons. But if they have the same number of protons, they're the same element. An element is defined, and might be something you might want to write down. An element is defined only by the number of protons in it. That's it. Not neutrons, not electrons, just the protons. And that is the atomic number. So each element has a unique atomic number that tells us what element it is. So hydrogen is the first element, so it has an atomic number of 1. Helium is the second element, 2, and then lithium, 3, and so on. That number here to the lower left tells us how many protons it has. So the number that appears above the block in the periodic table is the atomic number. Like, so we'll look at this a little more closely in a minute. The atomic number, for instance, for iron right here is up here at the top. And so we can see it is 26. So we know that all iron atoms have 26 protons. They have different number of electrons if they're charged. They may have different number of neutrons, but they all have the same number of protons. That's super, super important to remember. Now, mass number is different. The mass number tells you how big the atom is. So all atoms of carbon would have 6 protons because carbon has an atomic number of 6. But not all of the carbon atoms have the same number of neutrons. So carbon 12, we put the 12 up here. That's its atomic mass or mass number. So if we put 12 up there, that means that the nucleus has 12 particles in it. 6 of them are protons, and the other 6 would have to be what? If it's in the nucleus, there's only 2 things in the nucleus.
Neutrons.
Neutrons, exactly. There's also carbon 13. There's also carbon 14. Anyone know what we call these different forms of carbon?
Isotopes.
Isotopes, exactly. The only difference between isotopes are the number of neutrons in the nucleus. Everything else is identical. Same number of protons, same number of electrons. Everything else is identical. They just slightly larger or slightly smaller, depending on whether their mass number is a little bit bigger or a little bit smaller. So that's the difference. So don't get atomic number and mass number mixed up. Just think atomic means atom. That tells me what atom it is. Mass number tells me how big it is. Mass is weight. It tells me what the weight of that atom is. Is it big or is it small? So the bigger number will always be on top. The smaller number will always be on the bottom. So the larger number is always the mass number. Always, always, always. The smaller number is always the atomic number. Always, always, always. Because we can't have a carbon with less than 6 protons in it. Because if there's less than 6 protons in it, it ain't carbon anymore. So the mass number has to be larger.
Oh, isotopes are pretty much just, I mean, because you're saying the protons, they never change, but the neutrons, the number of the amount of the neutrons may change, and that would be like an isotope.
That's an isotope. It's still
Okay.
carbon. It's just a slightly different form.
Okay.
Yeah, still carbon. But like, for instance, carbon 12, almost 99% of carbon in the world is carbon 12. So like the vast majority of the carbon in you is carbon 12. And about around 1% of it is carbon 13. And then even a really super tiny amount is carbon 14. And we'll learn carbon 14 is actually radioactive. And so you have carbon 14 in your body right now because you've got carbon in your body, and it's a tiny, tiny amount of it. So the average, we'll get into this a little bit later as well, the average mass of carbon is a little more than 12. Why? Because there's carbon 13 and 14 out there. So if we took an amount of carbon and like actually counted the atoms and weighed them, we would see that their average mass isn't 12. It's actually a little bit more because of the presence of those other isotopes. And we're actually going to deal with, that's one of the problems in our set tonight. So just again, showing you the difference between atomic number and mass number. The atomic number in the periodic table is the one at the top. I know it's a little confusing. When you actually write the element, you put the mass number on top and the atomic number on the bottom. But when you actually look at the periodic table, the atomic number is on the top, and then on the bottom is the actual average mass. And that'll be really important a little bit later. That is the average mass. So basically, if I took a whole bunch of lithium and weighed it, I would find that it's not exactly what you would think. It's going to be a little bit bigger because there's other isotopes of lithium. There's other isotopes of carbon. And so when we're dealing with the mass of each of these elements, we have to take that into consideration because it's very, very difficult to get 100% pure sample of carbon-12. You can do it. It's a lot of work, but you can do it. But most of the time we're dealing with a mixture of different isotopes. So just once again, mass number just tells you the number, just think of it, it's the number of particles in the nucleus. That is the mass number. There's only two things in the nucleus, protons, neutrons. So we could always calculate the number of neutrons by subtracting the atomic number from the mass number, because the mass number tells us the total. The atomic number tells us the number of protons. And so the difference is the number of neutrons. We can always figure that out. And so here down at the bottom, we have iron. We would call this element iron 56. When we call a specific atom with a specific mass, we would just refer to this as iron 56. If we were going to write the symbol for it, we put the mass number at the top, the atomic number at the bottom. How many neutrons does iron 56 have?
30.
Mm-hmm. Almost always there's going to be more neutrons than protons. Almost all of the time. Not every time, but pretty much always more neutrons than protons because it helps keep the nucleus glued together. So let's determine the number of protons and neutrons present in a fluorine atom with a mass number of 19. How would we figure that out? What other information do we need to know to figure this out?
The atomic number?
That's right. So what's the atomic number of fluorine? I know you can figure that out because you've got your periodic table right in front of you. Right? I should have probably mentioned that. I should have made an announcement you should have them with you. But from now on, you'll have them with you.
Right, it's 9.
So fluorine, what's the... Oh,
9?
yes. Fluorine has an atomic number of 9. So where do I put the 9? The lower left or the upper left?
The lower left.
Lower, right. So there's my 9. There's my 19. So how many protons and neutrons does it have?
Nine protons and 10 neutrons.
Right, exactly. Now, sulfur, nice stinky sulfur. If it has 17 neutrons, what's the mass number? So for what information do we need about sulfur? Sulfur is easy to remember, it's just S. What do we need?
The atomic number?
The atomic number is sulfur. What is it?
16.
16, right below oxygen. So again, we put 16 there. That tells us that's the atomic number tells us the number of protons. So what would be the mass number we would put up at the top?
33.
33, right. So it's one more neutron than it has protons. Right.
So 17 neutrons and 16 protons.
So the total's 33. That total goes up in the top left hand, and then the number of protons or the atomic number at the lower left. So here we've already mentioned isotopes a little bit. Now, the thing to remember about isotopes is that they're the same element. So chemically, they pretty much react exactly like any other element. Like carbon-13 and carbon-12 participate in the same reactions. They share electrons the same. They do everything the same. So chemically, they're identical. Interestingly, though, there's some really important differences in physical properties. And one of the most important is the element here, hydrogen. There's three basic isotopes of hydrogen that you've probably heard of. One is just basic hydrogen. We actually have a nickname for this one. We call it protium. It just has and why? Because it has a single proton. So one proton, no neutrons, one electron. It is the simplest element there is. And in fact, I think it's considered probably about 90% of the universe is hydrogen. So yeah, there's a ton of hydrogen, much more than a ton of hydrogen in the universe, because it's so simple. And so the next one up from it in mass is if you add a neutron, we call this deuterium. Anyone know what's important about deuterium? Why is deuterium so important?
It's rare.
It's rare.
Well, 1 in 10,000.
Yep.
And it's heavier.
It's heavier. It is a very, very, very important historical place in history and still being used today.
Does it have something to do with the hydrogen bombs?
Yeah, it's heavy water. So water that has deuterium rather than hydrogen is given the D2O. Hydrogen in water is called H2O, just regular water. Deuterium, D2O, has the property of absorbing neutrons. It absorbs neutrons, and so you need it in the original sort of nuclear reactors. You needed it to slow down neutrons moving too quickly. And so when neutrons move too quickly, they wouldn't be able to hit the uranium atom very well and split it in two and release all that energy. And so if you use deuterium, the flow of neutrons is slowed down slightly, and so more of them hit their target, and so you get more generation of energy. You also get more generation of radioactive isotopes from the uranium, and so it's super, super, super important. In fact, there's a really fascinating history with the Germans during World War II making deuterium water, heavy water in Norway, and the Norwegians blowing it up. It's really, really fascinating stuff. So protium, deuterium, and then finally, when you put two two neutrons in there, you get tritium. Now, tritium is radioactive. Not super, super radioactive, but it is radioactive. And you can still buy watches today that have tritium tubes in them so that they glow at night. So the radiation from the tritium will hit the tubes and cause them to fluoresce. And so you can still buy them. There's a couple of companies still making them. I'm thinking of getting one because it sounds really cool. So that's where the isotopes are. Isotopes are only can change the nucleus, and they only change the nucleus with an addition of a neutron. So chemically, exactly the same. Physically, sometimes though, they're different.
I'm curious, if you get that watch, does it doesn't have enough radioactivity to harm you, right?
No.
Oh, okay.
No. And actually, the tube itself is coated with a
Mercury?
phosphorescent material,
Oh.
and then so there's phosphorescent material on the inside, but the tube itself is thick enough so the radiation can't penetrate it. So you don't actually come in contact with it at all. It's just basically all it does is just light up. It's just sort of like a neon sign. It lights up. So all neon signs basically are the same color. The only difference is they're painted with different fluorescent chemicals on the inside. So you get like red or blue or yellow or green or whatever. But the light that the neon makes when you pass electricity through it is all the same color. So it's the same principle here. So let's sort of briefly talk about radioactivity before we take a little break. So radioactivity just means emissions of either particles or high energy waves. So not particles, having no mass. Now they only come from the nuclei. They don't involve the electrons that are going around the nucleus. It is just the nuclei. And there's three main forms of radioactive emissions. One is the alpha particle. Now, alpha particle is a fairly large particle that's the equivalent of the nucleus of a helium atom. So it has 2 protons and 2 neutrons. So it actually has a positive charge. And it was one of the very first radiations that was detected. And it was detected because it was charged. And so you could put a couple of charged plates between it, and you could like move the beam of alpha particles around. And so that was basically how it was found. So when a radioactive atom spits out an alpha particle, the atomic number goes down by 2 because you've spit out 2 protons. And the mass number goes down by 4 because you've also spit out 2 neutrons. So a total of 4 nuclear particles are emitted. And it has a charge of +2. So that's the alpha particle. Alpha particles aren't particularly dangerous. They don't have really a lot of penetrating power. Interestingly, one of the most terrifying, radioactive elements after uranium is plutonium, right? Plutonium is an alpha emitter. So it's not that plutonium emits super dangerous particles. It's just that it's super radioactive, and it will split and break down into even more dangerous radioactive particles after that. So that's the first one. Next is the beta particle. So interestingly, the first one discovered alpha. That makes sense. Next one discovered beta. That makes sense too. It was also charged, but the charge on the beta particle was negative. And then it was shown to be an electron. So beta particles are actually electrons. And that screwed with people's heads when it was originally discovered, because there aren't supposed to be any electrons in the nucleus, but there are. Where do you think they come from? Just think of the two. What are the two particles in the nucleus?
Protons and neutrons.
Right. So we know the protons have a positive charge and neutrons don't have any charge. Why do you think that is?
Do they contain electrons?
Exactly. Exactly. So that's why the mass of a neutron is slightly bigger than a proton, because a neutron is actually a proton plus an electron. That's why it has no charge. It's because the two of them are stuck together. And so the proton, the mass of a neutron is the mass of a proton plus the mass of an electron. So when this falls apart, when one of the neutrons disintegrates, what happens is that this electron is thrown out, and basically the neutron gets converted into a proton. So what happens? So the mass number stays the same, because you still have the same number of particles in the nucleus, but you've switched one of the neutrons out and replaced it with a proton. So the atomic number goes up by 1. Now you have a new element because you've increased the number of protons by 1. Now the third one is a gamma ray. And a gamma ray doesn't have any charge at all. And in fact, it's just electromagnetic radiation. It's just a wave. But it's a highly, highly super intense energy. You probably know this, like gamma rays are basically X-rays. And so they just go right through your body. They're super, super energetic. And they're really, really dangerous, because they generally, what they will do is they will knock electrons, as they pass through you, they will pass through atoms and knock electrons out of them. And so they make them electrically charged. And what they do is ionize or turn into ions things that shouldn't be ions. And so they can cause a lot of damage. That's why you want to limit your exposure to gamma radiation, because it is the most harmful of any of these. Just by how energetic it is. So these are what we call the different symbols. So alpha has the alpha has this symbol. We call it alpha. That's how you make an alpha, like a little fish. We also use this name to it because basically it's helium without the electrons. So it has 2 protons and 4 total particles, and has a charge of +2. And so the penetrating power, very minimal. In fact, you can stop an alpha particle just with a piece of paper. It won't be able to penetrate it. One of the reasons why, because it's so charged and it's so much larger than everything else that it basically just bounces back. Beta particles, however, since they're just electrons, they're much, 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 much smaller. And so they can penetrate much further. So they will penetrate some skin and some tissues slightly. So you can get a burn from exposure to high amounts of beta particles. But generally, you probably, unless these beta emitters get inside your body, they're not that dangerous. That's where they're dangerous. Like if you inhale radioactivity, that's why, it's really important. People who work with these sort of things have, gloves and coats, and if you're working with like gases, certainly you have like a breathing apparatus. If they don't get inside your body, they're not really going to harm you. Gamma rays, on the other hand, will. It's just super high energy electromagnetic radiation. and will go right through you, causing a lot of damage as it does. So if you're dealing with gamma rays, really the only way to deal with that is to put as much space between you and the gamma rays as possible. That's why we generally encase things that emit gamma rays in lead, because lead is so dense that even gamma rays can't get through it. So that's why you see like lead shielding, or what we call, you probably, if you work in the hospital, you call them pigs, right? That's what we used to call them in the lab. You'd have a lead pig, which is just basically just a big lead container that you would put whatever your radioactive element inside, and it would basically prevents any radiation from getting out. Alpha, beta, or gamma doesn't come out of lead. So this just shows that again, like alpha stopped by your skin, beta will go through a little bit of skin, but it'll be blocked by like really thin layer of aluminum. Gamma will go through your hand, go through the aluminum, but then finally be stopped by lead. The other basic radiation that's emitted is just neutrons, just simple neutrons. And since neutrons have no charge, they basically just can penetrate anything. It's like neutrons are super, super dangerous. Anyone remember like the neutron bomb that was developed back, I think back in the 80s? People were all freaked out by the neutron bomb. Basically, it was an atomic bomb that just released a ton of neutrons. And so the design of that was the heat would be less, so you wouldn't see everything melt, but basically it would just kill everything with neutrons and nicely leave all of the buildings and everything else intact. So people thought, yeah, that's like super, super evil. Let's not do that. And I don't think that was ever developed. So these are how we write these nuclear. Oh, was there a question?
Yeah, sorry.
Yeah.
You went over it really quickly. You said I was actually curious, whenever you do x-rays, you always have to wear the lead coat.
Mhm.
So do you know the specific like mechanism of what lead does to prevent the radioactive rays to
Oh, it's
go
just
through your body?
super, super dense.
Okay.
It's just the density. Yeah, I mean, if you had enough water between you and gamma radiation, it would stop it as well. If you had enough, tin cans between you, but you just need a lot more of it. Basically, it's just because it's so super dense that the atoms are like super close together and super heavy. And so, yeah, basically the radiation gets blocked. Anything will block radiation if you have enough of it. I mean, if you had enough phone books, for instance, you could keep gamma radiation from hitting you, but you just need a hell of a lot more of them than lead. Okay. Yeah, it's just basically, the number, if you can throw enough large atoms between you and gamma radiation, it'll protect you. And just lead just happens to be super heavy and not radioactive. It's like pretty much, it's the biggest non-radioactive element we have.
I don't know if you heard this before, but there was a man in the 1900s. This is pretty interesting information. He had some sort of medical issue, so the doctor prescribed him radium, and so he continued to take it, and it helped. But it turned out it was, radium mixed with water, and eventually his jaw completely came off from the years of taking radium. And then when he died, he had to be encased in a lead encased, casket. And like 40 years after, they wanted to check to see how he was doing, and he was just as radioactive. So they were like, well.
Oh yeah, radium has a really, really long half-life, as we'll find out in a minute. There's also another really interesting story about radium. You might want to Google the radium girls. There is this tragic story of women who were painting watch dials with radium so that they would glow in the dark. And so they would need to use a really, really fine tip on their brushes to get the really super fine radium paint on there. And so what they would do is put it on their tongue, and then put a nice point on it. And yeah, most of them died of cancer the same way, with their jaws swelling up. But yeah, it was just awful. Yeah, back in the early teens and 20s, like even into the 30s, people thought that radioactivity was just the greatest thing. It was like, it's going to be super great. Radium was like one of those things you could buy. You could go into a drugstore and buy radium water. So because it was just, people would bathe in radium water because there's energy in it. And so, yeah, it wasn't until like a little later, like with the radium girls in particular, that they found that was not a good idea. A little goes a long way. So yeah, I would recommend. I might just put a link to that in Canvas, because yeah, it's such an interesting story. So when you're looking at radioactive decay, we look at it basically a decay equation, because something like uranium-238 will break down into something else, and then this product will break down into something else. And basically it keeps breaking down and breaking down and breaking down until it finally hits something that isn't radioactive anymore. Generally lead will be the last thing that these really large, heavy atoms will decay into, until it hits lead. And then since lead isn't radioactive, it'll just stop. So basically, if taken enough time, if all these super heavy radioactive elements become lead, and then they stop being radioactive. But we write an equation like this. So we give the mass number and the atomic number of the radioactive element, and then we show the particle that's emitted, and then what's left over. So uranium-238, which is the super radioactive. No, actually, no, radium-238 is not as radioactive as uranium-235, but it's still radioactive. And so it breaks down, it releases an alpha particle, and we're left with thorium. So all you have to do is basically add the atomic numbers and the mass numbers to go back to what the original one is. So whatever we're releasing, if we're releasing an alpha particle, we just subtract 4 from 238, we subtract 2 from 92, and that is the new element that's going to be left over. Okay, so the mass number of the reactant, so when you're writing a chemical reaction, this is a nuclear reaction, not a chemical reaction. We have our reactant on this side, and we have our products on the right side. So basically all you have to do is that the mass numbers of the reactant and the products have to be the same. And the atomic numbers have to be the same as well, okay? And remember to change the symbol if the number of if the number of protons has changed. If the number of protons has changed, now you have a new element. If the number of protons doesn't change, you have the same element as before. So like if it emits a gamma particle, for instance, it's still the same element it was before. So since gamma rays are just energy, you still have the same element at the beginning and at the end. This is an element that some of you actually may have used in the hospital. It's called technetium. I don't know if anyone's used technetium in the hospital. Anyone use that one? I guess not. Technetium is really interesting because it's the smallest it's the smallest element discovered that is just radioactive. There are no non-radioactive parts of technetium, which is still kind of interesting because it is in the middle of all these, it's completely surrounded by non-radioactive elements. So it's still a bit of a mystery as to why this small atom is radioactive, but it is. And so we give it this title, 99M. I'll tell you what that stands for in a minute. And then technetium, and it is 43. So what's the atomic number of technetium? Yeah, that's 43 protons. It has 99 total particles. So how many neutrons does it have?
56.
56, that's right. Now, the weird thing, like I said, about technetium is that all of it's radioactive. And basically, it has the reason why it's used in medicine is that it has an extremely short half-life. So basically, it has like a half-life, it's like I think it's only like a couple of hours. So you can give someone, like a fairly high dose of technetium, and then watch where it goes in their body, and then after 24 hours, it's gone. It's no longer radioactive. But we put the M here because it's what's called metastable. It's not that nucleus is not stable. And so it's emitting gamma rays. And when it emits gamma rays, it finally then becomes stable and no longer radioactive. Thing is, it's still technetium. Still has the same number of protons, still has the same number of neutrons, but it's now stable. So there's something in the way that the nucleus is set up that it is unstable until it releases all this energy. And then once it does, it achieves stability. And so a gamma ray, and this is how we make gamma, it's basically alpha pointing down. It has no mass, there's no protons, there's no neutrons, it has no mass. It's just super, super energetic. So technetium doesn't change. It just goes from being radioactive to not being radioactive anymore. And so technetium is basically made, it's synthesized in a nuclear reactor. So you make technetium in a nuclear reactor. Then once you've made some, you rush it over to the hospital where it's then administered. And like I said, you have to do this quickly. So you make it, you got to rush it to the hospital because it's decaying super, super fast. And then it goes away within a day. So we're going to do a couple of these questions. We'll do them together. So we're going to write a nuclear decay equation for radium-224. For americium-241, that's found in smoke detectors. So the smoke detector in your house actually has a small, really, really small amount of americium in it. And it's undergoing alpha particle decay. So right across from it is an alpha particle detector. And so if smoke gets in between, smoke with actual particles in it, like solid particles in the smoke, will block the detection of alpha particles and set off your smoke detector. And then finally, we have manganese-56 undergoing beta decay. So let's do the first one. So radium-224, that's a big element. So 224, what is that the mass number or the atomic number?
Atomic number?
That's the what?
Mass number.
The mass number, right.
Sorry.
Atomic numbers only go up to about, I think we're up to about 118 now. Scientists are constantly trying to build bigger and bigger atoms, because the idea is at some point, some people have a theory that at some point we'll get an atom that's so big it becomes stable again. So that's what they're trying to do. So I think we're up to about 118. And it's actually the Lawrence Berkeley lab here in the Bay Area. It's one of the major labs. The other one is in Russia, and the two of them are constantly trying to race each other to see who can make the biggest atom, because I think that one day they'll have a super big atom, and the whole world will thank them for it. Anyway, so radium. Anyone know what the atomic form, what the symbol is for radium?
All right.
Yep. Ra. Should make a small a. And so where do we put the 224? That go on the top or the bottom?
Top left. Yeah.
Yep, top. So what's the atomic number of radium? So that's one of the things you're going to need your periodic table for.
88.
What is it?
88.
88.
That's right, 88. So the 88 goes here. So when it breaks down, so here's our reaction. It breaks down and it's undergoing alpha decay, meaning it spits out an alpha particle. So if you remember, alpha particle is a helium atom, helium nucleus. So how many, what's the atomic number of a helium nucleus? What's the atomic number of helium?
2.
2.
2, right. And what's the size of a helium nucleus? You haven't really done that yet. It's 4. So remember, an alpha particle has 2 protons, 2 neutrons. So we say its the atomic number is 2, its atomic mass is 4. So what else? And it has a charge of +2. You don't have to include this.
I put both on the rest.
So what is left over? So basically we started with 224. We lost 4. So how many do we have left?
220.
220.
20.
220. Oh, wait a minute. Oh, it is 220. I thought it was 226. It's 224. Maybe I made a mistake. No, it is 224. Right, so it's 220. 220. And what is the atomic number?
86.
86,
Just
right.
radon.
So now we have to look up, yeah, so it's radon, right? You've already looked it up. So you look up, basically, you find what number 86 is, and you find out it's radon. Or RD, right? No, RN, I was right the first time. And radon happens to be a noble gas. So that's why radon is so dangerous, is because it's a gas. And it's still slightly radioactive. So radon then breaks down into something else. So that's why people are look for radon in like their basements, stuff, because there's a certain amount of radium, a small quantity of radium that is basically found naturally in concrete. Like people who dig up concrete, there's going to be a small amount of radium in there. Yes, Charlize.
I wanted to ask, how did you get the helium again? Like, where did it come from?
Oh, this is an alpha particle.
Okay.
That's just an alpha particle. So an alpha particle is a helium nucleus. So you're losing 2 protons and 2 neutrons. And it also has a charge of +2. So we add together 4 and 220, and we get 224. We add together 86 and 2, and we get 88. Right. All right, next one. So now we have our americium 241. So is this the mass number or the atomic number?
Mass
Always
number?
the mass number, right? Yeah, we always put the mass number. The reason for that is because basically we're telling you what the atomic number is by telling you what the element is, right? The atomic number defines what the element is. So by saying it's americium 241, we're already telling you what the number of protons or the atomic number is. It's the same as it's americium. So you just have to look up americium. So americium was, where do you think americium was made? Just take a
America.
wild guess.
America.
Uh-huh. Just like where do you think berkelium was produced?
Berlin.
Berkeley.
UC Berkeley.
UC Berkeley. In fact, UC Berkeley has at least 4 elements on the
Yep.
periodic table. There's berkelium, californium, seaborgium, and I can't remember what the other one. Maybe it was Einstein. No, Lawrencium. Duh. Made it Lawrence Livermore. Right. So americium. So we put the 241 up here. And what's the atomic number for americium? It's AM.
95.
95. Excellent. Now, that breaks down. Now, again, that loses an alpha particle. So remember what an alpha particle is. It is a helium nucleus with 4 total particles. 2 of them are protons. So what does that mean? What's left over?
Neptunium.
What would I write down? What's the mass of the product?
237.
Uh-huh. 237. And what is the atomic number of the product?
93.
93. Excellent. So now we just look at our periodic table and say which element is the 93rd element? Which is it?
Neptunium.
Neptunium. That's a good one. I forget whoever discovers these things, or in these matters, we generally these are artificial elements. These are ones that were made by bombarding one atom with another one, with a beam of another atom, basically hoping they stick together. So so neptunium, I think neptunium is a naturally occurring one. It breaks down from uranium-238, I think. So yeah, neptunium. It's a good name. So then the last one is going to be different. This one we have manganese 56. So what's the chemical symbol for manganese?
MG.
Nope, that's magnesium.
MN.
MN. There you go. Oh, damn it. MN. Yeah, that's a common mistake. Yeah, magnesium is Mg, manganese is Mn, and they're very similar chemically as well. So it has a mass of 56. How many protons are in a manganese nucleus?
25.
That's right. Its atomic number is 25. Excellent. So it breaks down into a beta. That's how we make a beta. It releases a beta particle. What's a beta particle? So if an alpha particle, remember, an alpha particle was big. It was the helium nucleus. Beta particle is much smaller. Remember what it is?
I forgot to take a screenshot of that slide, but it's you included it.
That slide? Which slide?
The one that had the.
Oh, yeah, I see someone, yeah, on Canvas. They're not PowerPoint files on Canvas. They're PDFs. And it is there. If you want to go to Canvas, it is there. But it's a PDF. It's not a PowerPoint. I can put it in the chat. All right, no problem. So anyone remember what the beta particle was?
I see it, but I don't know how to read it. It's like 0 and then a -1.
Okay, so it basically has very little mass and a charge of -1. What does that sound like?
An electron.
Yeah, it does. So it's an electron. So E. So it basically has no mass. And we know it does, but it's like 1/2000th of a atomic mass unit. So it's basically 0. And what is its charge?
This one.
-1. So it actually reduces, remember it changes, it doesn't change the mass, but it does change the charge of the nucleus because it is a charge of -1. So when we write the atomic number, basically what we're saying is it has 25 positive charges in the nucleus. An electron has a charge of -1. So when manganese releases an electron from the nucleus, what happens to the mass? What will the mass number of the new product be?
24.
Not the mass number.
What the?
Remember, the mass number is up here.
P6.
It would stay the same.
It's still 56. But now, right, the atomic number is different. So what's the new atomic number going to be?
Is it 25 minus -1 or is it 25 minus 1?
Well, remember, this has to add up to that plus that. So the products have to add up to the reactant. So whatever this number, so if this is X, X plus -1 has to equal 25.
So then it's 24.
No, I'm sorry. No, 25 equals, no,
6? Would it be 26?
26, right. Because if I take 26 and subtract 1 from it, I get 25. So this, again, this is where you have to have some solving for X power with you. So to solve this, we add 1 to each side, right?
Because like for the alpha one, you did the subtraction, right? You did, so this one, it's the same thing. It's 25 minus -1
1, right,
equals 26.
right.
Because, adding a negative
Mm-hmm.
and a negative equals a positive. Okay.
Yeah. Either way you want to look at it. Yeah. So this number plus this number have to equal that number. So the masses have to, the atomic numbers have to be the same. So 26 minus 1 equals 25. So if I have an element with a mass number of 56 and an atomic number of 26, what element is that?
Iron?
Iron, that's right. So basically you've turned manganese into iron by releasing that electron from the nucleus, because you've taken a neutron and turned it into a proton. So now I have a whole new element, and it's going to be, and the funny thing is it's going to be one bigger, one element larger. Even though the mass hasn't changed, the element itself has more protons in it. And so we say it's actually the next bigger element, though size-wise it hasn't changed. All right. Just a couple things to get through. Then we'll take a break. So these are just basic units of radioactivity. This is basically how we measure things. When you're buying some radioactive element, or you're buying something like when we used to, the lab I used to work in, we used to buy radioactive ATP labeled with P32. So you'd have to tell the company how much you want. And so we would get, that unit would be in curies. Now, who's that named after?
Marie Curie.
Yeah,
And
exactly.
I can't. Oh,
Yeah, she was the queen of radioactivity. In fact, she won 2 Nobel Prizes, one in chemistry, one in physics.
oh wow.
So a curie is a lot. A curie is a ton of radiation. Because yeah, you can see 3.7 times 10 to the 10 decays per second that's a lot. So that's how you would buy it. So you'd know how much product you had. Now these two down here are units of exposure. So they're completely different. Basically, they're like how much radioactive energy enters your body, how much exposure are you getting. So this is a unit of energy. Anyone know what the J stands for? It's a unit of energy.
Joule.
Joules, there you go. We'll deal with that a little bit later. Joules, it just basically says how much energy you have. And then, so that's a rad. You probably heard of rads before. That just tells you whether or not the radiation exposure is bad. But the most common one is REMS. Well, that takes into account what kind of radiation there is. So if it's alpha emissions, you don't really worry about those as much because, like I said, you could just put up a sheet of paper and it'll stop those. If it's beta radiation, then that's worse because that can penetrate further. So the REMS would go up. And if it's gamma radiation, it goes up even more. So it takes into account what kind of radiation it is. And the more active it is, the higher number of REMS you would be getting. So when you're calculating the risk of radioactive exposure, generally it's REMS we're dealing with. So half-life. Half-life super important because it basically tells us what that element is, because each element is a very specific half-life. Like P32, phosphorus 32, I remember had a half-life of 2 weeks. So when we were using it, if you didn't use it within like about 6 weeks, it was useless because then like the radiation it would emit would be so small that it'd be really hard to detect. And not many people use P32 anymore. We have much better ways of detection than radiation these days. But the half-life is just the amount of time it takes for half the decays to go away, basically. So half of that activity is now gone. So if I ordered 1 curie of something, of P32, 2 weeks later, I would have half a curie. And then 2 weeks after that, I have a quarter of a curie. And then 2 weeks after that, I would have 1/8 of a curie, and so on and so on and so on. So that half-life is constant. It is always the same. It doesn't change. It doesn't speed up. It doesn't slow down. It is always the same. And so we can always determine the amount of isotopes remaining just using this super easy expression. Whatever the initial amount is, and that's usually in curies, and then you just multiply that by 1/2 raised to how many half-lives? So it was 1 half-life, it's 1/2. If it's 2 half-lives, it's 1/2 times 1/2, which is 1/4. If it's 3, it's 1/2 times 1/2 times 1/2, which is 1/8. That it's always constant. So the amount that actually decreases gets smaller each time because we start with a large amount and then we get half and then half of that. So each time the amount that's left over gets smaller. But the time it takes for that to happen is always the same. Okay, so that's super, super easy calculation to do. Any questions about half-lives? Because you can see there's a huge variety of half-lives. You get something like tritium, and there's a half-life of around 12 years. So your watch will probably stop glowing in about 48 years, but then by that point, you probably don't care. Carbon-14 is pretty famous for carbon dating things. Basically, when you want to carbon date something, what you do is you see what the ratio is of carbon-14 to carbon-12. Because while you're alive, and this is going to be, a little morbid, but while you're alive, the amount of carbon-14 and carbon-12 is pretty much constant, because you're breathing it in and you're excreting it, you're breathing it in and you're excreting it. But once you're dead, then basically the amount of carbon-14 it's no longer in equilibrium with the outside world. And so this ratio starts to go down as the carbon-14 deteriorates. And so the half-life is around 6,000 years. So it's a really good way of estimating the date of things between about 600-700 years and about 50,000-60,000 years, and even more. The more sensitive detectors we get, the lower the quantity of carbon-14 we can detect. We can detect really small concentrations of carbon-14. So even a few million years we can use for carbon dating. You can see why uranium is so prized in reactors, because its half-life is in the billions of years. So once you've got uranium, you're good to go pretty much forever. The bad side of that is that when it becomes waste, if you want to use U-235 and then it breaks down into something else, the half-life of that is going to be incredibly long too. Like plutonium's half-life is billions of years also. So when you're storing radioactive waste, a lot of them have half-lives of billions of years, like longer than the Earth has been in existence. And so can you really plan on storing something that long? Other things that have extremely short half-lives, like look at seaborgium down here. So whoever made seaborgium over in the Lawrence Livermore lab detected it, and then it was gone in 4 milliseconds. So 4,000ths of a second, they were able to detect it, and then half of it was gone. So you can see that that didn't last a whole long time. So these are some of the effects of short and long-term exposure to radiation. So in REMS, again, because REMS are basically the best thing for determining exposure risk. So generally, you're going to get less than 1 REM in an entire year. Most people get about 500 millirems, which is 500,000ths of a REM, or around half a REM a year. So that effect, your body is equipped with ways to fix radiation damage. Each one of your cells inside the nucleus of your cell has enzymes that actually repair genetic damage due to radiation. The problem is when you get too much exposure, it overwhelms that process, and you get genetic damage, which leads to cancer and other things. But a small amount of radioactivity your body could easily deal with. So to give you some idea, a cross-country flight from LA to New York will expose you to about 2 to 5 millirems of gamma cosmic radiation from space. So not a whole lot, but you probably wouldn't want to fly every day of the year, 365. Then you'd start to get more exposure than you really should. So over 20 REMs, you get some small increase in some cancers, particularly blood cancers. More than 100, you start to get damage to white cell producing blood marrow, possible bleeding. You get visible burns, more than 200 to 300, and then anything more than about 500 to 600, you're toast. So that's just so try not to get exposed to that much radiation. All right. So here's the question we'll pretty much finish up with. So if I have a 10 milliliter sample of gallium-67, and that sample contains 15 millicuries, how many becquerels are present in the sample? That one is not particularly important to figure out. I'm probably not going to ask you that question, but in order to determine it, how many millicuries is that? How many curies is that? 15 millicuries. How many curies is that? How would I do the conversion between millicuries and curies? If I wanted to get curies at the end.
Move the decimal 3 places to the left.
Okay. But if I want to do it without making a mistake, how many?
By
1,000?
I want to get rid of, right. So where do I put the 1,000?
On the bottom?
Yeah, there's 1,000 millicuries in a curie. So that gets rid of my millicuries, and I'm left with curies. So that is 0.015 curies, right? And then the next conversion is between curies and becquerels. And so I want becquerels on top, curies on the bottom. And you probably don't remember, but a becquerel was 1 disintegration per second, and a curie was 3.7 times 10 to the 10th for every 1 curie. So we do the calculation, we wind up with 0.055 times 10 to the 10th becquerels. How would I convert that to scientific notation?
Be 5.5 times 10 to the 12th? Or sorry, 10 to the 8th.
That's right. If I multiply this by 100, boom, 10, 100, I have to divide this by 100. So when I divide that by 100, I make it smaller. So 10 to the 8th. Now, the more important question is, we have to, if we had to calculate a dosage, and the dose the doctor or the technician or whatever gave was it needed a 3 millicurie dose. How many microliters would be injected? So where do we start with that? I've got
So
10
we need to have a
mils. Oh, go
fifth
ahead.
of it? Is it as straightforward as it's a fifth of the 15? So it'd be a fifth of the 10?
Okay, so let's do the first thing. We'll figure out how many milliliters. So we've got 15 millicuries in 10 milliliters. So we have, and I want, let me just flip that around. So remember, I want milliliters at the end. So I'm going to put milliliters on the top, millicuries on the bottom. So I've got 10 mils and 15 millicuries. Right. So now I can just do the conversion and I get how many mils?
2.
2. So 2 milliliters is how many microliters? We just do another conversion. I want microliters now. That's the symbol for micro. That's the symbol for mil. How many microliters are in a milliliter? You remember what micro stood for?
It's 1,000, right?
It is 1,000. So a milliliter is 10 to the minus 3. A microliter is 10 to the minus 6. So the difference is 10 to the 3rd or 1,000. So there is 1,000 microliters in 1 mil. So how many microliters would we be giving for the dose?
2000.
2,000, right. 2,000 microliters. How many significant digits in that number?
1.
Just one. That's right. Because 10 has only one significant digit in it, and 3 has only one significant digit in it. So it's just the 1. Okay. So, oops. Said 1. Let me clear these. All right, let's do one of these, and I'll leave you to do the other one. So these are questions about half-lives. Oops. Let me swap them around. All right, so here I've got radioactive iodine 131. Has a half-life of just a little over a week. So if we start with 400 microcuries given to a patient, how much will still be there after 38 days? So how do we deal with this problem? You remember what the formula was? What do I multiply 400 by? It was 1/2 times a number. What was the n in that number?
Number of half-lives.
Number of half-lives, exactly. So how do we figure out the number of half-lives?
Just divide the 38 by 7.6.
That's right. So if I have
And it would be
38,
just a whole number, right? Because you wouldn't have a partial half-life, or
oh,
would
you could have a partial. You could definitely
Oh, you
have a
can?
partial. Oh yeah.
Okay.
Yeah, this is where this was where having a scientific calculator actually might help a little bit, because I don't think a simple calculator can raise something to the power of like 3.3 or whatever. But usually I'll try and keep it to whole numbers. So how many half-lives is that? Yeah, go ahead. Yes, Charlize, you know? You have a question or?
5.
5, right. So 5 half-lives have gone by. So n is 5. So I'm just going to make that a 5. So what is 1/2 raised to the 5th power? That's the same as 1/2 to the 5th power.
0.3125.
So what is it?
0.03125.
3125. So raised to the 2nd is a 1/4, raised to the 3rd is an 1/8, raised to the 4th is a 16th, raised to the 5th. So that's the same as 1/32, basically. So yeah, and so in your calculator will give you that number. So how much is left? So it's just 400 microcuries times this number. So how much do you have left?
12.5 microcuries.
Right.
I have a question. So, like, why, if that was a half-life of 7.6 days, why wouldn't you just put 7.6 instead of 5?
Because 7.6 days is one half-life.
Okay. Oh.
Yeah.
And then 38 days would be like
If the
more than
half-life
just
was a
one, right?
day, then yes, I would raise this,
Mhm.
then I would put 7.6 there, because that's how many half-lives there would be. So you have to
Yeah.
figure out how many half-lives there is.
Oh yeah, because like if you just put 7.6, it'd be wrong because there'd be more half-lives in 38 days for
Yeah, 38
Then
days,
just
there'd be
one,
38
just for-
half-lives, and there'd basically be 0 left. I mean, there'd be nothing
yeah,
there.
yeah.
Because yeah, 1/2 to the 38th power is pretty much bupkis. So there'd be very little left.
Yeah.
Okay, cool. All right, so let's take a like a 5-minute break, stretch our legs a little bit, and we'll come back and we'll work on worksheet number 2. Hopefully everyone's got it.